तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We introduced ourselves to the concept of Fourier series and to the evaluation of the Fourier coefficients an and bn which are required to set up the series. In many situations, the waveforms that we have to deal with exhibit certain types of symmetries which we can take advantage of and simplify the work involved in the evaluation of these various Fourier coefficients. This we will now take up for study under the heading symmetry conditions. We will talk about 4 kinds of symmetry and then see how each individual set gives rise to some advantage in the matter of evaluation of the Fourier coefficients. To start with, suppose we are given a periodic function which is an even function of time. The definition of an even function is f of t equals f of minus t for all t. Example of that would be, suppose I have a function which varies in this manner for positive t from 0 to t naught upon 2. In the negative direction, it takes for any particular t at minus t, the values must be the same. So, if this is a periodic waveform with this as the basic period, it repeats itself like this, and this is an even function of time. You recall that the basic Fourier series expansion is a naught an cos n omega naught t plus bn sin n omega naught t, the whole series of terms. Now, these trigonometric functions here of this a naught is of course a constant, it maintains its value, so we will consider that to be an even function. Cos terms are even functions of time, but sin terms are not even functions of time, they are odd. So, if this function is even, we can expect that we have no place for the sin terms in its expansion, because when you substitute minus t for t, the values of these terms will remain the same, but this set of terms will have their value reversed. Consequently, f of t can no longer be f of minus t. So, intuitively we can expect that all the bn terms go to 0. Let us prove this little more rigorously. So, if you evaluate b of n, you recall the expression for b of n is 2 upon t naught 0 to t naught, or I can also, for the sake of convenience in this regard, I will take this from minus t naught upon 2 to plus t naught upon 2, because this is more convenient for us in this context. F of t sin n omega naught t dt. I can break up this integral into 2 parts, 2 upon t naught minus t naught upon 2 to 0 f of t sin n omega naught t dt plus 0 to t upon t naught upon 2 f of t sin n omega naught t dt. Now we are going to show presently that this integral will be exactly the negative of this, therefore Bn will be 0. To do that, let me call this integral I1 and this as I2. Our goal now is to show that I1 is the negative of I2. So to this, let me evaluate I1 separately. I1 will be this expression, but now in I1 I will put x equals minus t. So I will change the variable of integration. Instead of t I use x, therefore dt will become minus dx. And since the variable of integration now is x, I must put the appropriate limits. So when t equals minus t naught upon 2, x will be t naught upon 2. And when t is 0, x of course will be 0. F of t will become f of minus x, and then you have sine n omega naught minus x minus dx. By virtue of this even character of this function, we can write this as this is t naught upon 2 again. F of minus x is equals to f of x because of this relation, and then sin n omega naught minus x will be minus of sin n omega naught x, and then you have another dx with a negative sign out in front. Now you see this negative sign and this negative sign can be cancelled, and if I interchange limits of integration, then I will get another negative sign. Therefore ultimately this will be minus of 0 to t naught upon 2. I interchange, that means you have got three negative signs, one by virtue of interchange as integral limits, one because the negative sign here and one here. I have got f of x sin n omega naught x dx. Now this integral here is exactly the same as this because it is a definite integral, and the variable of integration could be any value, it is a dummy index really. So this integral f of x sin n omega naught x dx could as well be written as f of t sin n omega naught t dt, which is indeed this, and because the negative sign out in front, this can be written as minus I2. So the upshot of this analysis is that Bn is 0. So if the function is even, we immediately can conclude that all sine terms are absent. This is the result that we get if the function is even. Naturally, we would like to ask, what is the corresponding result for an odd function? How does an odd function look like? If I have this as a variation for positive t, the negative t it will be like this. So if I say this is t naught upon 2, this is minus t naught upon 2, so this is f of t over a one period. Whatever sequence of values it takes in the positive direction of t, in the negative direction it will take the negative of those corresponding values. So f of t, we will say f of minus t equals minus of f of minus t, f of t, minus of f of t. Now if you again look at the general expression for the Fourier series, we observe that these are the terms which give rise to the odd character of the function, and these are the terms which are even. Therefore if you change t to minus t, we would like the entire function to reverse its sign. However, these terms a naught and a n terms will have the same value for minus t and plus t. Consequently, they spoil the character of the odd function, and therefore, we expect that these terms to be absent and only Bn terms will be present. And I leave this as an exercise for you to show in a similar fashion as here, that in this situation result is, I will not work this out, you can show it on similar lines, result is A naught and An terms are absent. So, when we see a periodic function which is an odd function of time, we do not have to spend time in evaluating A naught and Dn, we immediately know they are 0. So, all we have to do is work out the values of the Bn coefficients. A third type of symmetry which is quite important because it comes up in several occasions is half wave symmetry. Basically, what it means is that if you have a particular variation for half the period, the succeeding half period it will have exactly the negative of that variation. F of t plus t naught upon 2 is minus f of t for all t. Such waveforms are quite common, particularly in electrical machinery, when you have a rotor rotating and inducing the waveforms in the stator, whatever it is. Then alternately the conductors come under the north pole and the south pole, and whatever sequence of values for the EMF are induced when the north pole is in operation, the values will be reversed when the south pole is in under operation. Therefore, the waveform exhibits this kind of symmetry. The same set of values are reproduced with a negative sign in the succeeding half cycle. So, what is the offshoot? What is the consequence of this? First of all, we observe immediately that since the same set of values are occurring with a negative sign in the succeeding half cycle, the average of the period or the average of the function over the complete cycle must be 0, which means the DC value is 0. What are the conclusions? What other conclusions can you draw from this? This may not be evident, but let us work them out. Suppose I take An 2 upon t, and this time I break the integral for convenience 0 to t naught upon 2 f of t cos n omega naught t dt plus t naught upon 2 to t naught f of t cos n omega. By this time you must have got the idea of what we are going to do next. We would like to relate this integral with this. Therefore, for this purpose let us call this I1, call this I2. And we would like to compare the values of I1 and I2, making use of this result. Let me evaluate I2. In this, let me substitute x equals t plus t naught upon 2. Or rather x equals t minus t naught upon 2. Then I2 will be, so I am going to substitute x for t, dt equals dx, therefore the variable of integration is x, so I have dx. Then when small t equals t naught upon 2, x will be 0. When small t equals capital T naught, then x will be t naught by 2. So you can see now that the integral limits are corresponding to this straight away. F of t will be f of x plus t naught upon 2, because t equals x plus t naught upon 2, and we have in addition cos n omega x plus t naught upon 2 dx. That's what it is. Okay. Now this will be 0 to t naught upon 2, and see, by virtue of this relation that f of t plus t naught upon 2 is minus of f of t, f of x plus t naught upon 2 is minus of f of x. And then we have cos n omega x plus n omega naught t naught upon 2. Omega naught t naught is 2 pi, therefore this is n pi. Therefore this will be n pi. So this will be, I take the minus sign out in front, 0 to t naught upon 2. Now that I have outlived the necessity for use of x, let me go back to t, because after all this is a dummy variable, I can go back to t. This will be f of t cos n omega naught t plus n pi dt. Right? Now we have this n pi, we have to see what this becomes. So let us take two cases. Suppose n is even. If n is even, cos n omega naught t plus 2 pi, 4 pi and so on is simply cos n omega naught t. Therefore this will be minus f of t cos n omega naught t dt, which is the same as I1. Limits of integration is the same, the integrand is the same, therefore this will be minus I1. If n is odd, cos n omega naught t plus pi will be minus cos n omega naught t. 3 pi also is the same, therefore that it simply becomes I1. Right? So the upshot of this analysis is that this an turns out to be 0 for n even and 2 times I1 for n odd. Right? Therefore, finally, the conclusion that we have is all the A terms with even indices will become 0. Same analysis can be extended for Bn terms also. You can show that Bn will be 0 for even n, and for odd n, you see an for odd n turns out to be I'm sorry, 2in, I must also write here, because I am equating this, I must also multiply it by 2 by t naught. So I will write complete expression here. So this 2 by t naught multiplied by 2i1, therefore that means 4 by t naught 0 to T naught by 2 f of t cos n omega naught t dt. So, here also you have 4 by t naught 0 to T naught by 2 f of t sin n omega naught t. So, that is the result. We can summarize this saying that all even ordered harmonics are absent. So, when you have this kind of symmetry, as you have in the waveforms generated by electrical machines, you will have only the fundamental third harmonic, fifth harmonic, seventh harmonic and so on. You can't think of having the second harmonic, fourth harmonic, nor even the DC term, because the average is going to be 0. And for the evaluation of the odd harmonic components An and Bn, we have, instead of taking the integration over the complete period, it is permissible for us to integrate over half the period and consequently have 4 by T naught instead of 2 by T naught. That means you are taking twice the average over half the period rather than twice the average over the complete period. So, you can also dispense with a lot of integration and confine yourself to one half cycle whenever you have this kind of symmetry. Important that all even odd harmonics absent, and DC is also can be considered to be even harmonic, that is also absent. We have another kind of half wave symmetry. Where f of t equals f of t plus T naught upon 2 for all t. Previously f of t plus T naught upon 2 is minus f of t, now f of t plus T naught by 2 is plus f of t, which would mean the same waveform if you have for 0 to T upon 2, it repeats itself like this. Now, if you look at this closely, if indeed this is the situation that we have, strictly speaking we should have T naught by 2 as the period, not T naught, right, because we agreed that the period is the smallest value which satisfies this type of equation. Therefore, basically T naught by 2 is the period, which means the frequency of this is twice the frequency if we had considered this as one period. If we had considered this as one period, it is f naught. If this is the period, then it will be 2 f naught. So, consequently the frequencies present are frequencies that can be present are, you can have of course DC, 2 f naught, 4 f naught, 6 f naught, etc., where f naught is 1 over T naught. So, here you have only even even ordered harmonics are present. All odd harmonics are absent. Now, naturally you would question, why do you make a big fuss about this? If T naught is the basic period, T naught by 2 is the basic period, why not call that as the basic period, call that as T naught and then do with this? The answer to this, often we may have a particular waveform which we split up into a number of component waveforms, and in one of the component waveforms you may have this kind of symmetry. But we have to relate these frequencies to the original waveform from which these are generated. In particular, suppose you have an example from a sine wave, you generate, or okay, we will have not a sine wave really, suppose you have a waveform something like this, and then you rectify it, full wave rectification, you get this kind of waveform. So we would like to, whatever frequencies we present in this waveform, we would like to relate to the fundamental frequency of this. Consequently, we still like to have this as the basic period even when you are dealing with this, right. Therefore, in that context, if you persist with it, calling T naught here as the basic period, then in this signal you can have only the even ordered harmonics present, odd ordered harmonics are absent. The even fundamental will not be present naturally because it is the first harmonic. We will work out an example later which will illustrate this. So this is really a matter of definition, and if you call this, as far as this you want to deal with this particular waveform on its own without reference to any other waveform, certainly it is permissible for us to call this as the basic period and then analyze this in the conventional manner. But if you call this as the period for this waveform, then we can say that only the even ordered harmonics are present. These are the 4 important kinds of symmetry that one deals with. Also, it is interesting to note that if you have any given function f of t, you can always split this up into its even part and the odd part. So any arbitrary periodic function may not be even by itself, may not be odd by itself, but we can generate from it the even part and the odd part. So if you have f of t, you can call this f of t plus f of t can be written as f of t plus f of minus t upon 2 plus f of t minus f of minus t upon 2. So the first part is the even part, the second part is the odd part. So from any given function you can generate its even part and the odd part, and naturally the Fourier series of this will contain only the DC and cosine terms, and this will contain only the sine terms. So if you have the composite signal, the group A naught plus summation of A n cos n omega t corresponds to this, and summation of B n sin omega t corresponds to this. And it might be possible for us in some situations to break this up into its even part and odd part and find some additional symmetries in the respective parts. We will work out a few examples which will illustrate this. Put down some waveforms and let us find out first of all what kind of harmonic components are present, making use of the various symmetric conditions that we have discussed. Suppose we have this kind of waveform. Using the symmetry conditions, identify the terms present in the Fourier series, or you can say what are the terms that are absent in the Fourier series. So if this function is there, first of all you can straight away see this is an odd function because f of t equals minus f of minus t. Therefore only sine terms are present. And further, whatever waveform you are having here is repeating in the next half cycle with a reverse sign. Therefore this has the half wave symmetry of the type which we have talked about. So the result is that this can have only sine terms but odd harmonics. So odd ordered sine terms are present. In this waveform. You can't expect cosine terms, you can't expect second harmonic, fourth harmonic and so on, certainly not DC. Suppose I shift this waveform and have something like this triangular wave is symmetrically situated about the origin. Then what do we have? This is an even function of time, therefore cosine terms are present, but that half wave symmetry we talked about still persists. This whatever occurring in this half cycle will repeat itself, therefore we can say now it will have odd ordered cosine terms only are present. We must carefully distinguish between the oddness and evenness of the function and the oddness and evenness of the order of the harmonic, right. When there are cosine terms, you say it is an even function, when sine terms only is an odd function. That relates to the function itself, f of t and f of, whether it is f of t equals f of minus t or minus of f of minus t. What we are talking about is the order of the harmonic, the index of the harmonic, second harmonic, fourth harmonic or even ordered harmonics, and fundamental, third harmonic, etc. are called odd ordered harmonics. Suppose I have a function like this, which is the same function shifted upwards by a certain amount. So in other words, if I draw a line here parallel to the x axis and subtract this value from this f of t, this will be the resultant. So what do we conclude from this? It will have all the harmonics that we are having here plus a DC term, right. So you have, because if you subtract this value from this, then the resulting waveform will be exactly this, right. Therefore we have DC plus odd ordered cosine terms. Only will be present. So similarly, if this waveform is shifted up, so if this is a line, then you have, if you subtract that amount, this value from the waveform, you have a waveform which is given in A, therefore you have DC plus odd ordered sine terms. One thing you would notice from this example is that a same function, if we shift the origin, in one case it may be an even function, in other case it may be odd function. Therefore, the placing of the origin plays an important role, but that does not affect the amplitude of the harmonic, as we will see a little later. And once again, it is also possible for us to note that when you remove the DC term from a given signal, sometimes you find out certain characteristics which may not be present in the original signal, as this example shows. Now let us work out another example. So a waveform is given only for this interval of time. Now certain additional conditions are given and we are asked to find out, identify the complete waveform, right. So let us say the conditions are f of t has only odd ordered sine terms. So, if the waveform for the entire cycle is not given, only partial specifications are given, but this condition is given. So, this is the data that is given to us. So, if f of t has only sine terms, which means the function is odd. Therefore, if 0 to t by t naught upon 4 is prescribed to us, we immediately conclude that this must be its image on the negative time axis. So, this portion we can fill up because only sine terms are present. And then we are also given that it has odd ordered harmonics only, which again tells us that whatever sequence of values it takes in one half cycle is getting repeated with a negative sign in the subsequent half cycle. So, starting from this, in this half cycle this is the sequence of values, therefore, the negative of that would be this, and therefore, this also gets filled. Now, that corresponds to 3 t naught by 4. So, we have completed the waveform for a full cycle, right. So, we can make use of the conditional symmetry and then extend this to satisfy this the given data and the conditions that are given. So, suppose it is said that f of t has odd ordered sine terms. Cosine terms. Then how does it go? This is the waveform that is given to us, and since it has only cosine terms, it is an even function. Therefore, this would be the situation from minus t naught upon 4 to t naught upon 4, and since it has only odd ordered harmonics, this entire waveform gets repeated with the negative sign. So, this is the extension that we are having, and that would be the situation for a case where f of t has only odd ordered cosine terms. Let us have another example. We will take the square wave, which is a very important waveform. Of course, it repeats itself in the negative time also, like this. And we are asked to find out its Fourier series expansion. We can see straight away that the positive half cycle and negative half cycle have equal areas, they cancel each other out. Therefore, the average of this function f of t over a complete period is 0. Therefore, a naught is 0. We also can see, without further ado, that Bn is 0 because the function is, the function is odd, therefore An is 0. So, the only coefficients that can be present are the B coefficients. So, Bn would be 2 upon t naught, 0 to t naught upon 2. I will break up this integral into two parts. From 0 to t naught upon 2, the value of the function is a sin n omega naught t dt plus t naught upon 2 to t naught. In this interval of time, the value of the function is minus a sin n omega naught t. You can evaluate this second term to the two integrals separately and then arrive at the result. Alternately, we can also make use of one property which we have discussed already. When we are talking about half wave symmetry conditions, we said it's exactly the situation where whatever is happening in positive half cycle will occur in the negative side in the second half cycle. Therefore, at that time, if you recall, exactly similar situation, we said this integral is equal to this integral for odd n. Therefore, we can as well write this as for odd n, this will be 4 by T naught times this. Alternately, we can calculate this also independently. So, we can write this for 4 by T naught 0 to T naught upon 2 a sin n omega naught t dt for odd n only. We must be very careful in writing this. You can't have this and then evaluate for even n, it will give a result, but that is wrong. For even n, this term will cancel with this and that becomes 0. So, when you write this expression, you must make sure that you know that it is valid only for odd n only. This is 0 for even n. So, you work this out, then it will be Bn will be for odd n 4a by T naught 0 to T naught upon 2 sin n omega naught t dt. So, 4a by n omega naught t cos n omega naught t 0 to T naught upon 2, right. Therefore, this will be 4a by omega naught t is 2 pi, T naught omega naught T naught is 2 pi, so 2 pi n, and here you have 1 minus cos n omega naught T naught by 2. Therefore, this is 4a by 2 pi n times cos n omega naught T naught by 2 is cos n pi, and we are talking about odd n. So, cos n pi will be minus 1 and therefore, this will be 4a by n pi. So, only Bn terms is present. So, finally, we conclude that the Fourier series expansion for this would be right here f of t 4a by pi sin omega naught t plus 4a by 3 pi sin 3 omega naught t plus 4a by 5 pi sin 5 omega naught. So, this is a important result that it would pay us to keep this in mind. For a square wave like this with an amplitude a, the fundamental component has an amplitude 4a by pi. So, that means the fundamental will be something like this. The third harmonic will be having 1/3 that amplitude. So, it will be fifth harmonic will be 1/5. Actually, the figure which we have seen in the earlier lecture corresponds to this. So, the amplitudes go down inversely as the order of the harmonic. We will continue this discussion. To sum up, first of all, what we have learned in this lecture is that the symmetry coefficients, symmetry conditions on the given function of time enable us to calculate the Fourier coefficients with less effort than would otherwise be necessary. In particular, we saw if the function is even, then there can be only cosine terms present. If the function is odd, that if f of t is minus of f of minus t, only sine terms can be present. And the third type of symmetry that we talked about is when whatever waveform you have for one half cycle is repeated for the subsequent half cycle with its negative sign, then we call that half wave symmetry. It is quite common in electrical machines, for example, and in that situation we have only the odd ordered harmonics. We have the fundamental, the next harmonic is the third harmonic, fifth harmonic, and so on. There is another kind of symmetry which we mentioned in passing, that is when the function repeats itself identically for every half cycle. In that case, only the even ordered harmonics are present, that means the second harmonic, fourth harmonic, and so on. This, as I said, is, we call this function to have a period twice what we normally expect, half of what we, twice as we normally expect, because this is usually derived from another signal whose fundamental frequency is already defined. Using these symmetry conditions, we worked out a few examples which show how the Fourier coefficients can be evaluated, making use of the various symmetries that are present. In the next lecture, we will talk about another method of setting up the Fourier series, not in terms of trigonometric functions, but in terms of exponential functions, which will give a more compact notation and certain advantage in the computation. This we will take up in the next lecture.